Hi everyone, hope you're all doing great and really hope that January is treating you all well. So, welcome to everyone who is joining. Thank you for joining this workshop, and I really hope that this is useful for you. So, before we begin with this workshop today, I want to introduce myself. So, my name is Tooba Mukhtar, and I'm part of Pakistani Women in Computing Lahore chapter, and I work as the co-lead for the Learn department. And the main purpose of the learning series is to make sure that while you're all sitting at your home, you're all able to network with mentors and different people from the industry. Since when the pandemic hit, a lot of people started to feel demotivated about thinking that they might not have enough networking opportunities while sitting at home, and they might not be able to attend events and talk to people like they were just like they were able to do before pandemic. So the main purpose of the learning series is to enable networking and learning as well. The topic which we are going to cover today is basically the second episode of the learning series. And after we did the first episode, we did a survey and we asked a lot of you that what are the topics which you would like us to cover, and this is one of the most requested topics. So today's topic is frictionless data science, making the tools work for you. And the speaker for today's episode is Rabeez Riaz. So Rabeez did his undergraduate in computer science from Lahore University of Management Sciences, where his undergraduate research was in computer vision and machine learning. And right after that, he joined McKinsey as a data scientist, where he is working currently. So before I let Rabeez start speaking about the workshop, make sure that in case you have any questions about what is going on, if you don't understand anything, so do comment, as Rabeez will be answering all your questions towards the end. And of course, if if you're not able to hear Rabeez properly, do also comment that, so we make sure that that's not happening. And do take advantage of today's material. It's a really great and useful workshop, so make sure that you guys take full advantage of it. So over to you, Rabeez.
Um, Hi everyone, thank you for the nice introduction, Tuba. Like Tuba mentioned, we will be discussing. By the way, can everyone hear me? Tuba, can you confirm? Is my audio clear?
Yes, I can hear you perfectly fine.
All right, perfect. So, uh, like the name of the talk suggests, we will be talking about data science and the frictionless part. Um, I'll try to explain that with the small story. Um, it's really a quote. I was going through a statistics course by Richard McElroy. He mentioned something that really stuck with me. He said that doing statistics for a scientist is like riding the bus to work. Riding the bus has nothing to do with your job, unless you're a bus rider, in which case this metaphor doesn't really work for you. But whatever your work is, you have to ride the bus to get to the place you work and to be able to physically do the work. Um, they stuck with me because, like in my data science work, there's a lot of busy work involved. Um, Fighting with the tools, fighting with the data, and a lot of other slightly annoying things, which really don't have anything to do with data science, with data or science, technically speaking. But I have to go through those frustrating exercises so that I can get to the interesting business insights and generate impact. And I wanted to share some of my tricks or some things I learned through these frustrating exercises that help me navigate these things so that other people who are joining the field or have already joined the field um, don't have to go through the same struggles that I do. Um, so let me share my screen. Tuba, let me know when you can see my screen. So let's start. I'll just wait for a confirmation. All right, perfect. Um, I'm working in a Jupyter notebook. This notebook will be available on GitHub soon, like immediately after we finish this session today. I've made sure to list the version numbers of the packages I'm using. So if anyone has trouble recreating the examples, please do make sure you have the right package versions. And I'm not the best at writing down text explanations, but I've tried to explain what we'll be doing. So if somebody is going through the notebook afterwards on their own, hopefully you can get the same experience that we've we will try to give you in this live session. Um, So, like I mentioned, we will be going through some tips and tricks to streamline the data science workflow. We will cover some time-saving libraries, which just remove a lot of the busy work, I'll be honest. We will be covering some tricks regarding the pandas library, which is the de facto data manipulation and processing library. And there's a lot of really useful features built into pandas that I don't see people using that frequently. People try to um, implement those features on their own, and their version is not going to be as good or as flexible as the built-in one in pandas. I have a few examples of some features of the Python language itself, and I'll show you how those can be useful for your general workflow. Then we have something about like section 5 is about plotting, specifically about the Seaborn library, but at the end in section 5.4, I'll show you a couple of examples of other plotting libraries, specifically interactive visualizations. And section 6, if we get that far in the live session, it's about some, uh, let's call them advanced workflows with scikit-learn. Um, So let's jump right into it. First, let's cover the two data sets that we will be seeing a lot of today. I'm sure you will be familiar with the IRIS data set if you have done any sort of data science work in, I think, any language. The IRIS data set has four numeric columns which have to do with the flowers features, like the width and the length of the petals and sepals. Then you have some names of the flowers. There are three kinds here: Setosa, Virginica, and I think Indica. I might be remembering that incorrectly. And I created an integer column, which is just an encoding of this string variable into a number. This is useful for a lot of machine learning workflows. We will see this used later on. The second data set is the cars data set. I think this is a little more interesting, especially for data visualization exercises, because there's different kinds of columns here. We have a string column with surprisingly a lot of information. Then we have a couple of numeric columns. We have integer column for cylinders, and we have a date as well as a proper categorical column in the last column, which is the country of origin. So these are the two data sets we will use extensively as examples. So the first one is time-saving libraries. Like I mentioned, the theme of this section is to not reinvent the wheel. The first thing we're talking about is I want to say exploratory data analysis, but it's not really that. It's data diagnostics. I wrote it as data diagnostics over here. So what I mean by data diagnostics is exploratory data analysis doesn't really have a set goal. You're looking for patterns or things that you want to deep dive into. For data diagnostics, there is an actual goal. You want to understand the limits of your data set. What's the percentage of missing values? Do they have some pattern? Are there some encoding problems in your data set? Uh, what are the ranges of the numeric variables? I consider this distinct from the exercise of exploratory data analysis because there is an end goal. This is arbitrary distinction I've made for myself. Maybe you find this useful as well. But uh, like I said, yeah. So this is a like semi-contrived example I've created for the cars dataset. So the first thing you would see when you get a new data set is you might print the information, which will tell you the data types, the list of all columns, the number of null values. This will give you some overall idea. Okay, I have some string type columns, there's a date involved, there's integers and floats mixed, there are some missing values but not a lot. And then you might see, okay, for the categorical columns, what's the cardinality of those categorical columns? How many unique values are in each of the categorical columns? I only have two categorical columns: name, which has 311 unique uh, values, and origin, which has three unique values. So immediately I can see that, okay, name has 311 unique values, while the number of rows I have is 406. So I am going to have duplicate cars in this. But remember, I also had a column for the year of release. So I know a little bit about how cars work. So this is probably like a Honda Civic from the year 1970 and then a Honda Civic from the year 1971. That's probably what's going on. I can see the percentage split for origin. And one very common thing that people make, I'm sorry, I have zoomed in a little bit, so the plot's not really that easy to see. But this is a scatter matrix, and I'm seeing pairwise relationships for all variables. I can see that miles per gallon and displacement has a negative relationship. It looks to be slightly non-linear, but I can't be sure by just looking at this single chart. So in the next step, I might just take these two variables and dig a little deeper into that relationship. But this is a very standard workflow that you will go through for every new data set that you receive. And this is a very contrived example, and I haven't gone into a lot of depth. But I think this is still a lot of code, and more importantly, a lot of repeated code that you will do for every new table you get. And whenever you're repeating some boring task, instead of doing your actual job, which in this case is not to write code, but to find insights from the data, I think that's an opportunity for improvement. And the thing I want to bring to your attention is a package called Pandas Profiler. It provides an automated way to generate very detailed reports. It's just these two lines. I create the report object and I call two widgets, or there is an alternate function which is to HTML, and you can save that as an HTML file and email that to people, or whatever you may desire. So this code takes a bit to run. Mm, as you can see, it took 10 plus 5, 15 seconds. It took 15 seconds to run for this very, very small table. So if you have larger tables, this library will take a little bit to run. But keep in mind, how long will it take for you to write all that repeated code and for all that code to run? I think it's this exchange is fair with this library. I just write two lines, go and get a cup of coffee, and when I come back, I have this interactive report. Okay. So the first thing I see is the very simple things that df.info gave me: the number of observation, missing values, percentage. It even checks duplicates, which is non-trivial to check with pandas by default. It tells me the split of data types. I really like this tab. This is Pandas Profiler is trying to help me. It's given me some warnings that may or may not be important for me. So name has high cardinality. This means that if I so high card the problem with high cardinality variables is you can't really feed them directly into most machine learning models, because the simplest way to encode categorical columns is something called one-hot encoding, which means you create a new column for each unique value in the category. So I will get 311 columns. That's a lot. So it's warning, but I know based on my experience that I will not give the name column to any machine learning model unless I'm doing something with natural language processing, and that's a different topic altogether. So these warnings I usually find very useful. There's some information about how long the report took to generate. Now, the second tab has detailed information for each single variable. So let's check miles per gallon. It gives me the histogram, some diagnostics, some statistical information. Um, let's check another one, which is cylinders. Now it gives a histogram again and some the same diagnostic information. So this is immediately useful for me. I don't have to go through one by one for each variable and calculate these same things. It's done that automatically. Then there's interactions, which is the pairwise plots that I saw. It's done that all for me. And there's correlations, which is another thing commonly people do. It's done all the major correlations, and I think it's chosen appropriate. Yeah. So this is something that if you're not familiar with, when you create any kind of heat map, it could be a correlation or the adjacency matrix of a graph or anything. The color scheme you choose for that is very important. For correlation type matrices, which have a positive side and a negative side, you should always choose a diverging color palette, which has a neutral center point. As you can see, the neutral point here is white. A positive point, which in this case is blue, and a negative point, which in this case is red. So Pandas profiler has chosen the appropriate color value. It even tells me the count of missing values uh, in different forms of visualizations. I really like the missing value heat map. This particular table isn't a really good example for that, but there are different kinds of missingness in data. And depending on what kind of missingness you get, you have to treat them all very differently. You cannot, in all cases, drop the row or fill it in with zero or the mean value of the column. In a lot of cases, doing either of those is objectively the wrong thing to do. So looking at a visualization like a heat map of the missing values can help you determine what approach you should take to impute those missing values. Then there's a dendrogram. I actually don't know how Pandas Profiler makes the dendrogram. I've never had to use it, but it's there if you want. And it also does the head and tail of the table. So it's done everything that I used to do myself whenever I got a new table. Uh, and again, it's just two lines. Run those, let it make the report, and just go through the report and do the data science part, not the writing repeated code part. So the second library in a similar theme, it's about visualizations of machine learning models. Now, these could be diagnostic visualizations and exploratory visualizations both. The library is called Yellowbrick. Um, so I'll try to make the case for this library a little bit differently. So for anyone who's used machine learning in practice, any machine learning model in practice, could be a logistic regression or a neural network, doesn't really matter. You never implement those algorithms from scratch and use your custom version. I shouldn't say custom version, your own homebrewed version in production. You always use the version that comes with the scikit-learn or the version that comes with TensorFlow, because those are battle tested and actually tested and trusted versions, and you don't have to spend time recreating something that somebody else has already done better. That's the subtitle of this section. So it's the same thing for diagnostic visualizations for models. Those visualizations are designed to be very precise and specific. So you trying to make them, even though they could be very simple to make, like the ROC curve is not that complicated. You can make that in like a few lines of code. You can do the calculation and run the plot. Uh, but the ROC curve comes, the calculation at least comes with scikit-learn. So most people use scikit-learn to do the calculation, but then make the plot themselves, which I don't really understand. So Yellowbrick provides those plots, not only the plots, but also the calculation and customization that comes with them. So in this example, I've showcased a particular visualization, which is called the decision boundary. So for a classifier, the decision boundary is the point in which a classifier changes its decision. Now, if you don't know what a decision boundary visualization it's not really the point. The point is that whatever it is, it's been implemented and tested for you, and you can just use it, just like you use k-means from scikit-learn or some other model. So in this example, I created three models. a logistic regression, a decision tree classifier with default values, and a decision tree with the max depth of 3. So if you're familiar with how decision trees work, I've essentially regularized the last version in hopes that it generalizes better. So when ignoring the warnings, when I look at the decision boundaries, I can see that the logistic regression it looks to be doing reasonably well. It has diagonal boundaries. For both decision trees, I see that the lines are orthogonal to each other and axis aligned. This is a consequence of how decision trees work. And I can see that the second one has overfit like a lot. There's a single red dot, and it's created a box around that. The third one, I can see immediately that this one is performing much better than the second one. And I did not have to think of how to make the decision boundary calculations or the visualizations. Now, I personally have made the decision boundary visualization from scratch, and it's not the most straightforward thing. There's a couple of confusing things that happen when you're making this visualization that you have to keep in mind, which doesn't really have anything to do with your job as a data scientist who is supposed to figure out which model is performing better. Now, in practice, you are expected to write code to solve the problems that are part of your job. But my point today is that you don't have to repeat that code. You don't have to spend time fighting with the libraries. If you just change a little bit of how you think, then you can save not only your time, but also your employer's time and be more productive. So this is section 2 is done. Section 1 was the data set, so it doesn't really count. I'll pause for a second here to see if there are any questions. I don't think there are. Tooba, are there any questions? All right, let's move on. So the second section is about pandas. Like I said in the beginning, this is the standard um, data manipulation library. People use this to do uh, analysis on tabular data that can include filtering, subsetting, doing new calculations, aggregation statistics, all sorts of things. Um, so the first section is a little, well, it's not really about new features of pandas. It's about how you structure your own code. Um, so my headline here is code is communication. What do I mean by that? Code is communication with your coworkers and with your own future self. Um, people use this as a justification for writing comments, which is good. I'm all for comments, but sometimes people use comments as a crutch to write bad code. What I mean by that is, in a lot of situations, your code can clearly communicate your intentions, and you can use the comment for something more useful than just explaining what the two lines of code next to it do. You can use the comment as an opportunity to explain why you did your task in this particular way as opposed to some other way, instead of just explaining what your complicated bit of code does. Now, pandas code isn't the most complicated thing in the world. But I'm sure if anyone has used pandas, they've written lines that look like this. This is a very simple, straightforward operation. I take the cars dataset, filter on a single GA, then I group by the origin and calculate the mean. Now, by default, it calculates the mean of all columns, and I see it like this. For each country of origin, I calculated the average value of all the columns. Now, on surface, there is nothing wrong with this line of code, and it's fine. But when you're working with more complicated data sets and doing more complicated calculations than just calculating the mean, this line suddenly becomes something that's twice or three times the length. And at that point, this this becomes completely hard to understand, not only for yourself but for other people who are going to read your code. It was very easy for me to figure out that, oh, the first part is filtering, then there's a grouping, and then of course there has to be an aggregation at the end, and that's me. But if this line was twice or thrice the length, that it wouldn't be that straightforward. So I'm proposing an I'll zoom in a little bit. I'm proposing an alternative way to format these lines. Now, this is in no way my discovery or invention. I saw this somewhere online and I really liked it, and I have used this ever since. So if you put parentheses around the line that I showed you above, this line, then you can break each individual step into its own line. And this is valid Python syntax. And most reasonable IDEs or code editors will help you format the line automatically if you start it like this. Now, immediately I can see that I'm working on the cars data set. The first thing I'm doing is a filter. Then I'm doing a group by, and the aggregation is a mean. Now, I really like this approach because I can do things like this. If I want to check what the difference between a mean and a median would be, I can write it here. Now, I comment mean and I run the cell, it works. I come and I swap the, and it works, right? And this is very useful for me, at least, when I'm testing different things inside the same cell. Another thing I can do is, let's suppose I'm sorting the columns. This sorts the columns alphabetically. Um, for some reason, let's suppose I wanted to sort the columns at the beginning. Now I have a keyboard shortcut which swaps lines above or below. I can easily work with this structure of code in that. So there are a couple of reasons why I like this structure, but the most important one is that it's very easy for me to follow the operations which are happening on the table. We use the term data pipeline. I'm sure people have heard it, even if they're not data scientists. This is a very common thing that people say. A data pipeline, it communicates that something is happening in sequence, one after the other. And I think this way of writing code actually communicates the idea of pipelines very nicely. So this was my section 3.1 about code as communication. So the next one is a natural continuation of the pipelines ideas. These are just two helper functions. This one just calculates the mode of a pandas series. The second one, I'll show you what it does in the next cell. So this is, again, a very normal bit of pandas code. If anybody has worked with pandas, they most probably have written code that roughly looks like this. So I'm filtering on a year, then I'm creating a new column from the name column. I'm taking the first word, and that's usually the manufacturer of the car. So Honda Civic, the first word is Honda. Those are the people that made the car. This function, I'm giving it the data frame and some arguments, and it's giving me back another data frame. So what this function is doing is it's giving me all cars which are made by the top 10 manufacturers. There's some logic in that function, but it's not really relevant. But what matters is that it's a function which takes in a data frame and outputs a data frame. Then I'm doing some aggregation. Now this one is a bit, this aggregation is a bit more complicated, but I would argue more realistic. I'm grouping by two columns, and I have different aggregation functions for each of the three columns I've selected. And I'm also renaming the resulting columns. Now, when I rename the columns, by default, what pandas does is, it keeps the old name and writes the new name below that. That's not really what I want. So I drop the first sort of level of columns. Now, if you don't know what this function does, don't worry, we'll cover that in the next section. But this is some piece of code in pandas that's doing a relatively common operation. And this is the result. It's I like to call these pivot tables, but the people who use Excel consider something else a pivot table. We'll see that in a little bit as well. So this is the result. Now, there's nothing wrong with this code, but again, I'm proposing a different way to write the code. This is my proposal. Now, on surface, this looks more dense and more confusing, but trust me, it's not the case. This only looks more scary because I've removed the comments and the nice empty lines in between. This is exactly the same code, just written a little bit differently. So it's using the parentheses trick I talked about in the previous section. So I start with the cars data frame. do a filtering operation, calls this assign function, which is making a new column. So that's all that matters. Calling this pipe function and giving it the function that I used on the pandas data frame above. Now, this is a very useful function for you for structuring code in this pipeline fashion. That it's not a coincidence that the function is called pipe. So this function takes in a data frame and a function, calls that function on the data frame and returns the resulting data frame. And I do a grouping operation on that data frame, do the same aggregation, do the same drop. And of course, I'm getting the same result because it's the same logic. But again, for the reasons I talked about above, this is much better because I can move lines around, I can comment them, and this looks better to me because it communicates the idea of a sequential set of operations. Um, I'll pause for questions. Are there any questions? There was a lot of code in this section. So I'll wait a little bit if there are any questions before moving forward to more code. I don't think there are any questions though. Okay, let's move on. So the next section is about multi-index in pandas. So for people who don't know what an index is, if I print the data frame here, these numbers you see on the left-hand side in bold, the 0, 1, 2, 3, this is the index. And I can get it if I do cars.index. It will give me the range index that starts at 0 and stops at 406. Let's double check if that's true. Starts at 0 and at 406. It's non-inclusive, just like the range in Python, so it checks out. But there are actually two indices in a pandas data frame. One is the row index, which you get by calling cars.index. The second is the names of the column, which are themselves an index. You get to them by calling df.columns, and as you can see, it is an object of type index, but it's on the columns instead of the rows. So what's the point? Why are these useful? If somebody is coming from a database background, I don't have to explain to them why indexes are useful. But the indexes in pandas are work a little differently from indexes in an SQL database. Um, they are used for lookup, similar to databases. They do speed up lookup by a significant amount, but there's another thing. It's about how you interact with the table itself. In databases, you rarely interact with the index directly. The index is something that's for most operations working in the background. The pandas index, you have to interact with the pandas index directly whenever you want to do any kind of filtering operation which you want to be fast. So let's remove the cell. So this is a simple aggregated table that I've made. I've grouped by two columns and done the mean, and this is the result I have. Now, if I call index on this, notice that this time it's a list of tuples. For a default table, the index is just a list of numbers. But in this case, I grouped by two columns. So the index, as you can see here, contains two things, right? It contains Europe and 4 for the first row. And that's what I see. The first row is Europe 4. The second row is Europe 5. The third row is Europe 6, and so on. So the index now has two values for each row. Similarly, I can do a multi-index series. If I select one column and run it, I get a multi-index series instead of data frame. But if I look at the index value here, it's the exact same thing that I got above for the multi-index data frame. So the index is an independent object separate from the series or data frame that it is attached. Now, why am I talking about the index? Why is this useful? I hope you're familiar with two operations in pandas, the .loc and .iloc. The loc stands for location, and the iloc is integer location. These are the two recommended ways of accessing a particular row or series of rows in a data frame or series. If I call loc using Europe on the aggregated series, I get three values with the second level of index attached. Now, it makes sense to me at least. If I pass in the full tuple, Europe comma 4, which was the first row, if you remember. I get the value of the first row, and it checks out. This is it's the first value. Now, if I give it just Europe, it gives me all rows which start with Europe. If I give it Europe comma 4, it gives me the row which is uniquely identified with Europe comma 4. But what if I want all the rows which have 4 in them? The reverse of this operation. Hmm, I can't directly give it 4 here because it will try to look for 4 in the first level of the index and it won't find it and it'll give me an error or an empty list. I don't remember exactly. So the way to do that is there is a general function called XS. I don't know what this stands for. This is a generalization of the loc operator. You can give it a value and tell it which index you want it to work on, either index or columns. Okay, and you tell it the level. So level starts from 0. Level 0 is the country. Level 1 here is the cylinders, and you can see the names over here. Okay, so if I want all rows which have a value for 4 in cylinders, I give it 4, tell it look in the row index and on level 1, which is cylinder, and it gives me the 3 rows which have an cylinder value of 4, and it gives me the values and index. So these were simple lookup operations on multi-index. Um, Another natural thing that you might want to see, I'll reprint the series over here in case people have forgotten. The another thing you might want to do is swap the order of origin and cylinder. So I want the cylinder numbers here and I want the country over here in the second column. There's a function that does it. It's called swap level. Now let's see what happens when I call it. It swaps the values, but it doesn't group them together. So there's a 4 here, there's a 4 here, there's a 4 here. I want them to be grouped, right? So the most natural thing here to do is just sort the index. It sorts both levels. Now they're grouped. This is usually what I want when I do swap level. Swap level combined with sort index. Another thing, this is a function I used in the previous section. It's called drop level. And as the name suggests, it removes a level from the series. If I tell it to work on axis 0, which is the row axis, I can also give it axis index as a string. It works the same. And the level 1, which was the cylinder level, it removes the cylinder numbers from the index. If I give it 0, it removes the country index but leaves the cylinder. So this is also a useful thing. Now notice it hasn't combined the 4. Even if I sort the index now, hasn't combined the 3-4 rows like it did over here. Now, this is just a visual trick that Jupyter Notebook is pulling on you. If you actually want to group things together, you have to call group by again. Now, the reason why I talked about multi-index so much is because I truly believe it's a very, very useful and underutilized feature of pandas. People get confused when they see indexes. They usually do filtering directly on the columns instead of putting them on indexes. And when they get a large table, um, and they have to do some cross filtering, then their code suddenly becomes slow and then they're confused what's happening. That's where indexes come in. And multi-indexes are useful for a second thing, which we'll see in section 3.4, and that's pivot tables. If somebody isn't familiar with the idea of a pivot table, this is it. Pandas is a function which makes it. I give it the data frame, tell it which variable to put on the rows, tell it which variable to put on the columns, and tell it what function to call to aggregate. Here I'm calling the size function, which is just the number of rows. So for Europe in 1970, there were 6 cars that were made. For Europe in the 1971, there were 5 cars that were produced. This is essentially what a pivot table is. And if anyone has done any kind of work in Excel, any kind of actual work in Excel, you might have come across somebody who's made a pivot table. All right, this is what they mean. This should look very familiar to you, to a group by operation on 2 columns, right? Not in terms of structure, but in terms of the information it contains. Because if I group by origin and year and call the aggregate function as size, it should give me the same answer, right? And let's see what happens. For Europe in 1970, there were 6 cars produced. For Europe in 1971, there were 5 cars produced, and so on. The information that's contained here is exactly the same, but the structure is different. So there's a function called unstack, and obviously there's a function called stack as well, which does the reverse. It takes a multi-index from the rows and puts one of those into the column. You can specify which one you want to go and which one you want to move to the column. By default, it's -1, which in this case will be 1. If I do it, now these two are identical. I prefer this group by way of making pivot tables to this pivot table function. It's just my personal preference, but it's important that you understand that this data processing operation, which is general, it's not even a Python or program. People do this in Excel all the time. It's exactly the same thing that you can do with group by, and this should uh, this should be important to you if you come from a databases background, because you have group bys which work very nicely in SQL, but the SQL pivot table is very strange and doesn't really do what you want it to do most of the time. So you can use this to create pivot tables, and hopefully this equivalence between the two things is useful for you um, in your work. The next section is about tidy data. Uh, by the way, a lot of examples and concepts are obviously not my own. I'm not that smart. So the the places I learned them from, they're mostly YouTube talks from PyData or SciPy or some other conference, or just some random tutorials. I've tried to link them all in the text here. So this section has a couple of examples which are from Daniel Chan's talk. I think this is a PyData talk. Might be remembering this wrong. It's about cleaning and tidying data in pandas. Now, in English, cleaning and tidying is the same word, but in data science, these both mean little different things. So, what do I mean by tidy data? Let's start by a simple definition. So, I will consider a data set tidy if it has three properties. I think it's three properties. Let's see if I remember this right. One row corresponds to one observation. One column corresponds to one feature or variable that I'm measuring. Right? If I'm measuring three things like temperature, air pressure, wind speed, then I should have three columns, right? Or three variables. That's what I mean. And the third point of the definition is that one cell. No, actually, the third point for tidy data isn't relevant for this example, so I think we should leave it. The third point is each measurement has its own. No, not each measurement. Each data source has its own table. I think that's the third one. But that's not relevant to this example, so let's keep it just to the two. So I'm using this table. It's a very simple table to understand. Getting it directly from a URL from Daniel Shen's GitHub repository. This is an example of an untidy table. Now I'll explain why. Let's try to understand what this table contains. Like what pieces of information does it contain? Obviously, the first column is religion. It's agnostic, atheist, Buddhist, Catholic, etc., etc. So this is about people and what religion they follow. Okay. The columns have dollar amounts, and it's now I know because I checked this table out that these are income brackets. So 27 people in this data set are agnostic and have an income of less than $10,000. 34 people are agnostic and have an income between $10,000 and $20,000. Okay, this is a pivot table. It should be very obvious to you because we just saw an example of pivot table in the previous section. This is a pivot table. Now, the reason this data is stored in the form of pivot table is because pivot tables are very easy for humans to understand. It's very easy for me to read out what this data contains. I just did, right? But the structure of a pivot table is not helpful for programming libraries to do general purpose data manipulation or analysis. There is another structure which can contain the same information, which is called a tidy data frame. Uh, Most data processing and plotting libraries prefer to have their data in a tidy form. And in the next couple of sections, and the plotting section in number 5, I believe, we will see why that's the case and how it can help you. So let's try to convert this into a tidy data frame. Now, there were 2 points in the tidy data frame, right? One row is one observation and one column is one variable. So how many variables do we have in this table? One, of course, is the religion, right? It's already in a column. The second is the income bracket. These columns should all be in one column with the name of income or income bracket. The third column is the values in these cells. These values denote the number of people. So there should be a third column called number of people. So 3 columns in total: religion, income, and number of people. And of course, if I reshape this table in this new format, it should have more number of rows. I hope that point is clear. This table is too wide, which is why we call this a wide form table. And I'm converting it into a long form or tidy table. Now, in pandas, there are two functions, melt and pivot table. Melt goes from wide to long, pivot table goes from long to wide. Um, if somebody has used R, and specifically the tidyverse set of packages, there are two functions, gather and spread, which do the same thing as melt and pivot table, sort of. They're from the package called tidyr, which is a fantastic name for a package that does tidy data frames. I prefer the interface that gather and spread provide. Melt and pivot table work a little differently because well, the reason isn't really that important here, but I just wanted to mention that if somebody is confused by what these functions are doing, and if you know a little bit of R but haven't worked with gather and spread for some reason, try to learn those first and then come to these functions. At least that helped me understand what the point was. Okay, so this is the code. I call pd.melt, give it the data frame, tell it which column is an ID column. What this really means is, in the original untidy table, the religion column was already in a column. We don't have to do anything with that. That's all this means. So I tell it the religion column is already in a column, don't do anything to it. Now, then the value columns are the ones that should be turned into one column. Now, I've given all the other columns as an argument here, but since these are all the columns except for religion, I don't have to give this argument. Pandas by default takes all columns except for the ID vars and puts them in value vars. And I can name the resulting columns as well. So this is the result. One column for religion, one column for income, and one column for the number of people. And the number of rows here is 180. In the old one, it was 17. So yeah, this is a tidy data frame. So why is this a tidy data frame? The first part of the definition was a single row is a single observation. One row is the agnostic people who have less than $10,000 of income. How many? 27. The next row is atheist people who have less than $10,000 of income. 12 people, and so on. This is a tidy data frame. If you have your table in this format, the data manipulation libraries will be easier to use. The filters and aggregations will have a consistent structure in terms of code. You will not be confused by if I'm filtering by this variable, I write code like this, but if I'm filtering by this variable, I have to write code a different way. I've seen people get frustrated when they have to do that, but the only reason that they have to do that is because their data is in an untidy format. If you spend the time to convert it first, then the library will help. The library is designed to work with tables in this format. And it's the same case for plotting libraries. People try to make very complicated, relatively complicated plots, and they get frustrated. And this is why, if I'm sure people who have even dipped their toes into the world of data science will have heard the um, classic fight of R versus Python and the argument that R has superior plotting capabilities. The reason, well, we'll go into the details of that in section 5, which is the plotting section, but it has something to do with tidy data, a little bit of a spoiler. So now I have the table in a tidy format, but there's still some cleaning I can do. If you notice at this column, this one doesn't have a dollar sign, and that annoys me a little bit because all other columns have a dollar sign. So let's fix that. And what else? Yeah, where did it go? Yeah, evangelical prot. This is evangelical Protestant, and I want it to be the full name. So let's do that. I use the string accessor, which is learn the panda string accessor. This will save your life. You won't. This will free you from a lot of for loops that people have to write. I replace prot with protestant. Second thing, I use np.where to convert this string into this string. Um, Another thing, there's a data type called category in pandas. Um, this is very useful if you have a high cardinality categorical column and you want to save space. Just convert it into category, and for most situations, it will work like a string, but it will consume very little memory for most situations. You have to be a little careful. But here, why I'm using it is because I can create something called a sorted category. I give it the order I want it to be in, which is numeric order from smallest to largest and the missing value at the end. I tell it to keep this as an order. And now if I look at the column, I have the values here. The type is category, and it remembers that less than $10,000 is smaller than 10,000 to $20,000, and so on and so on. This is an ordered category. So if somebody has worked with R, the categorical type in R is called a factor. And it's been a while since I've used R, but I'm pretty sure you can have ordered factors as well. So this is the same thing. The reason I'm doing this is because whenever I do grouping operations, I prefer to have, or even plots, I prefer to have my categorical variables in a particular order, which means something for my business case. In this scenario, it's very simple. It's literally just the numeric ordering of the incomes. But in other scenarios, there could be that for your business, if they have three products, they always keep the three products in a certain order in visualizations or reports. So I would want to keep them in the same order as well, and this helps me to do that. Now, an example: if I want to do a filtering operation, and yeah, okay. So if I want to do a filtering operation, I want all Catholic people who have an income level of less than 10,000, and how many are there? No matter how many variables I have, the syntax will remain the same. I will just keep adding one more condition by doing and. If the dataset was not tidy, I could not do this. I would have to use a combination of this filtering syntax and block, which becomes a huge problem once you have many data sets and all of them have different formats. Just convert them into the same format and your code will be more easy to understand for yourself. Um, the other thing is grouping. I can group by income, get the number of people, sum. So how many people have an income of less than $10,000? 1,930 people. Now, if I call sort index, it's using my sorting order, not alphabetical, um, because don't know refuses at the end and all the numeric order is maintained. So this was about tidy data frames. The next section is about date time functionality in Pandas. So this is another thing. Date time is a little bit of a niche topic, relatively speaking, in data science. A lot of people have to work with tabular data, but a subset of them have to do time series analysis. So most people don't know, but Pandas was made by like Wes McKinney. He's the original author of Pandas. He used to work at an investment fund when he made this. So, needless to say, in quantitative finance, time series analysis is a very fundamental part. Um, so, the first sort of features he added into the Pandas library had to do with date time and time series analysis. So, they have native date time types, which we saw in the beginning when we looked at the cars dataset. The year column has a data type for date time, and it somehow has a precision for nanoseconds, which is not useful for us in this exercise, but it is there. Um, uh, the dataset I loaded was already converted into a date time column, but if it is not converted into a date time column, um, you can convert it to a datetime using the pd.to datetime function. It takes a string, which I've done here. I've converted the here column into a string and converted it back into a datetime using the to datetime function. You can see they're both identical. Um, the example I'm going to use here is of aggregating over dates. So I can do a group by and give it the year column, use the datetime accessor, and just get the integer year. So I'll show you what this does. Actually. This is very useful. If I just do the years column, this is it. The DT accessor gives me access to the individual features of the date. I can ask for the year. I can ask for day of week. I think I don't remember exactly what the name of the function is. Weekday. Yeah, weekday. So weekday. This tells me what day of the week was it. Weekday name. So there's a lot of features in. So if I do dt.year, I have the integer value of the year, and I'm giving it to group by. So I'm grouping by the year and the country and how many cars were produced. It's the same example as in section 2.4. So I can do the same thing using a different function called resample. Resample is like group by, but it knows that it's working on a date. This will become important in a second. So I can recreate the above example exactly by doing group by origin, then resample on year column by a single year in call size. Let's remove this for a second. This is the answer. By default, it keeps the full date, the entire date string. I really just want the year column, so I have made a helper function to format the columns. Um, and I have the exact identical result. All right. So why did I like what's the point? I got to the same output with more code and some confusing helper function. What's the point? The point is now I just grouped by a single year. In 1970, there were 6 cars made in Europe. Now, if I want to group by 2 consecutive years instead of one, how will I do that in this group by structure? I leave that as an exercise for you to think of how you will do it. But if you use the resample thing, the only thing you have to change is add a 2 over here, and it will automatically do the aggregation for you. Now, um, this example isn't 100% correct because you need to check uh, that the calculation is actually working correctly. And here, what's happening is it's keeping the first column, the first year separate, and it's adding year 2 and year 3 here. So there's some work to be done on the second column, but I can immediately increase the number of years or any time frequency. Like I can do it by months or years or whatever. So resample is very useful whenever you're working with dates and have to do some statistics. There are some other features of the pandas library which give you very specific functionalities like date offset. I've had to use date offset exactly once in my work, and it felt like it was made for exactly that scenario where I used, which it was most probably. And it saved me a lot of time because if I had to implement that functionality myself, it would have been a very horrible experience because not only would I have to implement the functionality, I would have had to test that I implemented it correctly. But I can be assured that date offset in pandas is working correctly. Let's pause for questions. Are there any questions? It doesn't look like there are any questions. All right. Uh, okay, sorry. I misunderstood. We're going to do questions at the end. Um, hmm. I'm going to skip section 4 and 6 because I really want to go over plotting here because I feel like that's a common pain point people have, especially when working with pandas, with Python. Sorry. So the language features I was going to cover are generators and context managers. I gave a couple of examples of making your own generators and context managers to solve specific problems that you come across. Um, I encourage you all to go through the notebook and try to understand the examples. I've given text explanations of most of what I was going to talk about. And we will be skipping section 6 as well. I create a custom imputer and a custom classifier in section 6.1 and 2, and use the relatively new pipeline and column transformer interfaces from scikit-learn. So if you want to see how to structure code in scikit-learn, you can go through section 6. There is nothing to do with machine learning algorithms or new techniques in this one. It's just code structuring and features that the library gives you to structure your code. So let's jump ahead to section 5. Section 5 is about, okay, bit of a spoiler. Yeah, section 5 is about plotting. There's no need to fight with the tools. This comes back to my point that I was making earlier about R versus Python, and people considering that, the main argument people have is that R has a much superior plotting mechanism, and they're talking about ggplot. If somebody doesn't know what ggplot2 is, ggplot is I'm pretty sure it's the most famous. Easily it should be one of the most used R packages. I haven't checked, but I would be surprised if it's not. It's a plotting package, and the reason people like it is because of the name a little bit. The GG in ggplot stands for grammar of graphics. Um, and the point I try to make in this section, section 5.1, is, well, one, to explain what the grammar of graphics is, and I'll give you a brief overview here. It's a very deep topic, and I've linked to a talk, which I think is a good, concise explanation of what the idea is and why it's powerful. I'll try to convey it in fewer words here, but I don't think I'll be able to do it justice. The grammar of graphics is a way to think about the mechanics of your plot. It's not about the calculations or the statistics that happen behind the scenes, but it's about how you represent the idea of the plot you want to make in a language, which is why it's called a grammar. It doesn't have anything to do with R or the library ggplot. The concept is independent of any particular programming language or package. So this pyramid, I really like this pyramid diagram. Let's start from the bottom. The For any data visualization, the first thing you need is your data. So this is an obvious thing to say. The second thing is what here is called aesthetics. On the right hand side, there is some explanation for this. The axes, the XY axis, the positions of the plots, and the encodings. Now, I'll tell you what encodings are. The next thing is scales. Is it a linear scale? Is it a logarithmic scale? What is it? Then you have geometric objects. This should be familiar. Lines, bars, points. Then you have some statistics, which is mean, quantile, confidence interval, and there's some other things beyond that. But the reason I like this pyramid visualization is it very clearly conveys that there is some kind of layering effect going on here. You need the lower level things in order to create a complex visualization, and you need to understand each step, right? And for anyone who's worked with ggplot, this terminology should be very familiar because, like I said, ggplot is the R implementation of grammar of graphics. That was exactly what it was made to be. And the my thesis statement here is that the reason people prefer plotting in R is not because of ggplot specifically. It's because the most popular plotting paradigm in R is the grammar of graphics. Unfortunately, the most popular plotting library in Python, which is the de facto matplotlib, it predates ggplot and the popularization of the concept of the grammar itself. I think matplotlib was the first public release of matplotlib was made after the book about the grammar was published, but it the idea wasn't. I don't think the idea was that popular back then. There's some historical reasons about why matplotlib is the way it is, but it's not really relevant here. If you are curious about the history of the PyData ecosystem, I've linked to another talk. um, I find the history of programming environments very interesting, but I don't think most people will. So let's see what the grammar of graphics brings. Yes. So my issue with the argument about R versus Python and people bringing up ggplot is that people are comparing ggplot to matplotlib when they should either be comparing base R graphics to matplotlib or comparing ggplot to Seaborn. Seaborn is the most popular statistical plotting library in Python. It is Um, I I'm pretty sure I don't know what the intention of the author was, but to me it seems like the Python implementation of the graph, similar to what ggplot is for R. And I'll show you why. So this is some test data that we will use for plotting. I've just taken the cars table and done some aggregation. It doesn't really matter what it is, it's just a table with the year and the columns are country. Now, it should be obvious that this is not in tidy format. If it was in tidy format, I would have three columns. One was year, the second would be origin, and the third would be number of cars. Now, in this untidy format, pandas can make plots. I just take the data frame called plot.line, and it makes a line plot with legend and labeled axes and colors automatically set. Now, this is a very nice looking plot, all things considered, and it's very easy to make. It's literally three words. um, but pandas is the only sort of like pandas gives this functionality for free, and it does a lot of jumping around hoops, around the hoops matplotlib creates. Um, but if you have to modify this chart, uh, it's not that straightforward. The pandas gives you some features as arguments here, like the this quarks thing. You can control a little bit of how the plot looks, but not a lot. So let's convert this into a tidy format. I'm again using melt, and this is the tidy version. Now we will start using Seaborn. This is a table I made. I think this something like this table should be in the Seaborn documentation, but it's not. So I made it myself. Um, where did it go? Yeah, these are the axis level plots. So familiar things: scatter plot, histogram, line plot, sorry, box plot, bar plot. There are some unfamiliar things like what's a boxen plot or what's a swarm plot, but Seaborn has a lot of things. So, and I've written in the rightmost column corresponding plots, which I'm calling figure level plots. So I'll explain what I mean by this in a second. So let's try to recreate this plot using using Seaborn, and I will show you how it is implementing grammar of graphics in Python. Uh, so obviously I want a line chart, line plot. I give it the data frame, I give it the X is year, Y is number of cars. Now I get this strange thing. The reason I'm calling this strange is I was expecting something like this. Now I know I haven't specified that I want the color and origin, but uh, without that, I at least expected there to be one line. But this line looks weird. It's and what's the shaded region? So by default, what Seaborn is doing is there are two arguments, estimator and CI. If you're confused by what's happening here, I urge you to look into the documentation and see how these two arguments work. But the gist is, if I look at the first data point, it's on the year 1970. If I check, I have three data points here. So what Seaborn is doing is it's taking the average of these three numbers, plotting it as the line, and taking the confidence interval at this point and plotting it as the shaded region. That's what Seaborn is doing. That's not what I want. So I give it hue origin. Hue is color. And now the shading has gone. The reason the shading has gone is because for a given year, each country has only one number. So Seaborn is trying to calculate the confidence interval in the background, but there's only one number, so it doesn't make sense. But now I have the exact same plot as before. And now if I look here, this is what the grammar of graphics was about. There's the data, there's the aesthetics, which is columns or features from the data mapped to visual properties of the chart. The x-axis has the variable year, the y-axis has the variable number of cars, and the color variable has the variable origin. And what kind of plot is this? The geometry, it's the line plot. Now, ggplot has a slightly different syntax to this, but if somebody has actually used ggplot, I'm willing to bet you can see the similarity. And now another very common thing that people do and a useful thing that the grammar provides is this idea of facets. Um, it's based on the idea of small multiples, and it's very useful. In ggplot, you just add a facet layer. In Seaborn, it's slightly different. Now, the only thing I've changed between this cell and the next one is I've changed the function. Instead of line plot, I am using rel plot, which is a relationship plot. And since now it doesn't know what kind of relationship it is, I'm telling it that I want a line. This is a figure level function for line plot. If you go back and look at the table, you will see what I mean. Now, visually, this plot is exactly the same, almost, Just a second. Um, yeah, visually this plot is almost exactly the same. The aspect ratio is a little different, but the contents are identical. The reason why I did this very useless change is because rel plot can take arguments for col, which is column, and row. If I give origin on the column, now it has made a new column for each country. If somebody has tried to make subplots using matplotlib and got very confused about what is happening, um, firstly, I sympathize with you. Secondly, I would argue that for most use cases, you don't really want to create subplots, you want to create facets in the statistical and grammar of graphic sense. So just use Seaborn. Don't worry about matplotlib. Now, it sounds like I hate matplotlib, but it's not really the case. I actually really like matplotlib. I don't know if that's Stockholm syndrome setting in or what, but uh, to prove that, I've implemented the same plot using just pure matplotlib syntax. I have to create the subplots myself, tell them that the axes should be shared, give it the size, the number of columns. Then I have to loop over all unique countries and create a separate plot for them and label the axes. This is a lot of code. Not only that, it's a lot of busy work. Like, I know there are three countries in the origin column. Why can't the library just figure out and make three plots for me? This is what people expect matplotlib to do. But Seaborn does that. And Seaborn was designed to do that. Matplotlib was designed to do something else, which is out of the scope of this exercise. But like, having those expectations from matplotlib is unfair, especially when you have Seaborn. Um, Again, repeating my earlier point, this would be the same thing as you saying that base graphics does not have a very nice, easy to use faceting interface in R. Um, Anyway, that's my point about facets. Now, just a couple of other additional things. Section 5.3 is me. Uh, yeah, if you look here at the rel plot thing, the return value is something called a Seaborn facet grid object, which is a little strange. What's a facet grid? What happened to the plot? So you can create the facet grid object yourself. You can manipulate it. You can add things to it manually. Here, I'm adding a global average line on all plots and adding it to the legend on the right as well. Um, in a lot of cases, when you're doing facets, you usually want to compare them against some baseline. At least that's very common. That's a very common thing that I have to do. So, and you can work with the facet grid object directly, but I don't recommend it. Um, yeah, this section. I think people will like this section. So the title of the section is "This Philosophy Pays Off." So if you understand the grammar of graphics and understand it beyond the syntax of ggplot or seaborn, understand what it's trying to do, then what you get is you get a lot of very interesting things for free. Number one, Plotly. Plotly is a very popular interactive plotting library. Since it's interactive, it has to be based on JavaScript, but uh, it has an interface which is very heavily inspired by Seaborn. It's called Plotly Express. I've imported it as PX. This I'll copy the code actually. This is very similar. It's the first time I saw this, I was very surprised. I like, what is happening? So this is the Seaborn code. Seaborn code, and this one is the Plotly code, Plotly Express to be precise. Actual Plotly code is not this nice to look at. So this is like super identical. I just changed the name of the function. Instead of data, I call it data frame. And instead of hue, I have color. Instead of call, I have facet call. And that's the only difference. Like literally, I've used this to my advantage. I use the Plotly version to do exploratory analysis. Then I just change these values to make the Seaborn chart because there are other reasons in that exercise that I wanted to see portrait, but it's super strange. So this chart is completely interactive. I can zoom in, double click to reset. Double click to reset isn't working. Click on this button to reset. I can zoom into the region between 1975 and 1980 only. All right. I can remove USA from the plot. Like this is just a full-fledged Plotly plot, but it's made using the interface, which is similar to Seaborn. Inspired by grammar of graphics. There are other libraries as well. Yes, we're still in the Python ecosystem. Fix this 300. Yeah, that's better. So this is a library called Altair. This is a relatively new library, but I like it for a couple of reasons. Here, I think this syntax is I prefer the syntax of Altair even more than the ggplot syntax because it's a lot cleaner. But it's the same idea. I set the x to here, y to number of parts, color to origin, and column to origin as well. I tell it that I want a line chart, and I tell it that I want it interactive. It makes the chart with subplots, with legend on the right side, and it's interactive as well. I can zoom in, zoom out, drag, and everything works. Double click to reset. Everything works perfectly fine. So understanding the grammar of graphics concept and the tidy data frame concept will not only make your life easier with ggplot or cbond or whatever, but it will also make it easier for you to learn other tools which are designed to be very simple. And section 5.5 is about an interactive sort of small scale interactive thing. I've made a very simple dashboard. I can change the bin size, I can change whether the x-axis is log scale, and the plot updates, right? um, the 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 thing I want to explain here is not that this is a fancy dashboard, because it's not. I mean, look at it. But that I made this using things that come pre-installed when you install a Jupyter notebook, and I have never seen anyone use this. Like, I've seen one person use this in somebody I was working. I've obviously seen this used online, but this functionality comes pre-installed with Jupyter notebooks. Like, you don't have to pip install or do anything, and this comes pre-installed for exploratory data analysis. I think this is super useful, and I wish more people really use this, because they would really understand binning bias, at least if they use this for once. Like I said, I'm going to skip section 4 and 6. I know I rushed through the plotting section a little bit, but hopefully when people go through the notebook themselves, they have they can understand the idea that I was going for. That's all I wanted to go through. I think we have time for questions. Yeah.
So thank you, Rabeez. It was really helpful and I really enjoyed it. It was really interesting. So hopefully the audience enjoyed the session as well. So let's go through the questions. We have quite a couple of questions. And one of the most common is that how do we get the material or notebook or the link for your repository? So maybe you can share it. Rabeez, I think you're on mute. So
Sorry. You have the link. Let me just make the repository public. I forgot to do that last night.
yes.
Uh,
So we will
public.
be sharing the link of the repository and Rabeez GitHub link with you as well, like in a minute in the comment section. Okay. So the
Yeah, the
second
link should
question.
work now.
Okay, so the second question is that were we supposed to have a link to the data set? So do you have the link to the data set in the notebook, or maybe you can guide the audience?
No, it's the standard iris and cars datasets. If you don't have these, you can get a link from somewhere, or like in the notebook. Actually, what I do, there's a very nice package. It's a very simple package. It's called Vega Datasets. It was made by the same guy who made Altair, Jake Vanderplas. It You can use it to download datasets, like the standard datasets from. I think it gets it from the UCI ML repository or something. The packages used in the notebook, in my notebook. If you just install that package, it should work fine.
Okay, great. So the next question is that for a multi-class problem for logistic regression, how do we choose the right metric?
Hmm. Do you mean the optimization metric or the metric you're going to report? Because those are two
Maybe,
different things.
yeah, maybe you can answer in terms of both.
Hmm. Mhm. So for the reporting, I think the reporting answer is more interesting, because the optimization one is there's right and wrong answers for the optimization one, and it's been long enough that I've done a multi-class logistic regression that I am pretty sure I'll get the answer wrong. But it should be some a variant of the uh, what's it called, cross entropy loss. Some I don't remember if cross entropy by default works with multi-class or not, but I think that's something you can look up, and there should be like one or two correct answers. For the metric that you have to report to people, like the performance metric, how good is my model? Since it's a classification problem and it's multi-class, um, one thing that I found useful is to have decile wise, class wise precision and recall scores. It's not a single number, which is mostly what people want, but it gives me the opportunity to talk about areas where the model is performing better and worse than other areas. And it's simple enough that non-technical people can understand, because if I take a decision boundary diagram to them, it's the conversation is over before it even starts. So that's a compromise that I have found to be useful.
Okay, sounds good. The next question is from Hezra, and she's asking that R versus Python, what do you suggest to learn considering current industry trends?
So I'm assuming it's learn first, because whichever one you start with, once you get to a certain point, let's say you start considering yourself an intermediate user of that language, because it's you're not really learning R or Python. You're learning R and Python for data science. It's very different thing. Um, so once you get to a reasonable enough threshold, you understand what a group by is. You know that there's a concept of a data frame, and you can do filtering on it, and you understand the ideas of tidiness, etc. You can switch between languages very easily, right? Like I consider myself to be a Python programmer even before I started doing data science. And like most, like 95% of the work I do is with Python, but I don't understand what you mean, Kudat. Can you explain? Sorry. So if I will give the diplomatic answer. If you're coming from a CS or engineering background, I think Python will be easier to start with, because it will be similar to other languages you've seen. R was made like specifically for statistical stuff. Or non-CS background, I think learning data science in R is relatively more easy, because the barrier to entry is a little lower. For Python, you need to know a couple of other things of how general purpose languages work. Um, but the payoff at the end, I think, is better, because of the fact that Python is a general purpose language. But in practice, if you're doing just data science work, yeah, you can go either way depending on your background and which one you personally find easier.
Okay. So the next question is that what kind of projects should I put to present good impression on resume?
Uh, so hmm, I have to think about this a little bit, because it's most of the online tutorials or even the boot camps, the projects they have you do are either very basic, or they've been done by so many people that you having that project on your resume can be considered a negative thing, or at least it's lost its value in recent time. Um, so what I would suggest is, um, which is a bit more difficult than just following a tutorial online, but I think the payoff will be worth it. What I would suggest is pick a domain or a topic or a data set that you like. Um, Try to find a data set for the domain or topic. If you can't find it, try to think of ways you can measure or capture that data set. Now, I know for a lot of domains and topics, you literally can't do that, but for a lot of them, you can actually. You can scrape websites. You can have some kind of scraper or some script to measure things on different websites and stuff like that, and then just do some analysis on that, just to answer your own curiosity. it doesn't really matter if you didn't use the cool algorithms or very in-depth statistical analysis. It doesn't really matter. Try to follow your curiosity with that data set and topic, because it was supposed to be a topic that you're personally interested in, right? And during this process, you will learn a lot more than just following a random another tutorial on the Uber rides data set, or Airbnb housing data set, or something random like that. That would be my advice.
Okay. So the next question we have is that what's the roadmap to become a data scientist? Which tools we need to study?
Hmm. Huh. Okay. Hmm. I don't think there is anything new or useful that I can say to answer this question, but like whatever tool you're using, it doesn't really matter if it's R or Python or Tableau or even Excel. Like, it really doesn't matter. I do surprisingly a lot of work in Excel in my actual job. Like, I didn't think that would be the case, but now I realize that it's whatever tool gets the job done in the shortest amount of time. That works. Um, so I wouldn't really be focused that much on the tools. Like I said for R, like check out both, because it's so easy to see some random video on YouTube, like, oh, R in 30 minutes, Python in 30 minutes. Like, I'm not making the claim that those are good videos to learn R or Python, but just watch those videos to see what R and Python are like, get an idea, and see, oh, this thing looks like I would like it better, or something, and just start. And there's a lot of uh, similar things for tools as well. Um, like, there's standard tools. By now, the domain, like the data science domain, is relatively mature, sort of. So the tools are kind of standardized, like plotting in R, ggplot. Data manipulation, if it's for general purpose data science, it's the tidyverse packages, dplyr, and all those. If it's performance is a concern in R, I think you use data.table. I know Tooba uses R more than I do, but in Python it's the same thing. You use pandas for like 99% of the things you do, and whenever you have to make a plot, usually Cbond has you covered. So it's less tools you have to worry about than people actually realize.
Okay. So the next question is that given data, how do you know which machine learning model to use and choose the right parameters?
Hmm. So it's two separate questions. Choosing the right parameters, you can never know. You always search. Um, so it's an easy answer from my side. You never know. I mean, you can have some idea based on experience. Oh, like that. The max depth should not be more than a 5 for this particular task for a decision tree, let's suppose. But you don't know if 3 will be much better than 4 or whatever. So you have to search at the end of it. You can't answer that beforehand. The other question is a bit more interesting. Like, knowing the data set, which machine learning model would you choose? I think that's the wrong way to look at it, at least in isolation. The choice of machine learning model you use is mostly dependent on the task and the real world constraints, more so than it is dependent on the data. The information you get from the data set about the model is very trivial. It will be like, oh, like I have a lot of data, or I have uh, like uh, I don't have any numeric variables, so using just a logistic regression probably isn't going to work that well. So it's in the grand scheme of things, that decision is trivial. What's important is you understand what the business goal is, what the task is, and what the actual real life constraints are. Does this model have to run multiple times a day, and it has to run online? Oh, does okay. If that's the case, the model has to be fast, really fast. Um, and you might know of a very fast neural network, but if your company or employer or client or whatever does not have the infrastructure to use that very fast neural network, it's not going to be useful, right? So you'll have to choose a different model, not because the data changed, but because the real life constraints force you to pick a different one. So I think that focusing on the actual business task and the real life constraints are much more important in the choice of machine learning model, or even if you should use a machine learning model at all. Like, that's also a valid answer in a lot of situations.
Yeah, I think the last point is the most relevant or important one, I would say. Okay. So moving on, the next question is from Umar, and he's asking that I am practicing data science from last year, but I'm unable to get any internship. What do you think that what should I do and what practices I should adopt?
So I don't know Umar's background. I don't know where Umar was applying or what Umar's resume or profile looks like, but I'll it's basically the same answer I gave for the projects in the resume, right? Um, Actual data science work isn't really figuring out which model to use in what scenario or like knowing what metric to use. A lot of that stuff can be googled very easily. I usually don't, like, nobody I've worked with remembers which metric to optimize for. Like, that's not what we do. The actual things that we do that are trying to solve a very weird problem that doesn't really seem like it can fully be solved. So my job is to figure out how much of it can we solve, and is it going to be useful to solve just that much. And that's why I mentioned, like, follow your curiosity with the data set, right? And that will give you interesting stories and point you in interesting directions. And the reason why I'm bringing this up here, like, it seems like I'm giving a random answer, but when you go for an interview, if you just have like another Uber or Airbnb dataset project that you just followed a bootcamp or tutorial to do, that's not really, like, six candidates out of the 10 in that for that particular job would have done something similar to that. But if you go over there and say, okay, I didn't really do in this project, there's not some sophisticated machine learning, I just did a k-means cluster at the end. But this is I'm really interested in video games. Oh, I got the Steam dataset from the last couple of years, and I scraped StreamDB and got the historical prices. I was curious to know how much an effect do Steam sales have on uh, like the Steam discounts have on video game sales. And I try to answer that. Like, this is not a question that you will answer by using any machine learning model. Like, you will have to actually go out and look for the data. I try to figure out what problems are in that data, apply your own domain expertise as a person who plays video games on Steam, right? And that's the kind of things that will, I think, impress an interviewer more than just another Airbnb project. I know I'm ragging on the Airbnb dataset. I actually like it. Um, and it's a good exercise for geospatial stuff as well. Yeah.
Okay, so the next question is that how do we handle the columns with NaN?
Hmm. That's it.
Yes, that's it.
It's a very, very broad question. That's why I was hoping there was some additional detail there. Um, so I mentioned in the beginning, like, as a cursory note, that there's three kinds of randomness: missing at random, missing not at random, missing at random, missing completely at random. The solutions people usually apply, which is dropping the rows or filling with the mean value of the column or something similar, are technically only valid solutions for missing completely at random. And for most situations, you're like, if you have missing values in your table, it's for some reason. It's not completely at random. So there's no silver bullet. You have to understand why your data is missing, what could be the possible causes of it, and can you recreate the process to fill in those blanks. Like, if we got to section 6, the example I show for the custom transformer is an imputer. Like, if you know, for example, that this particular column has to be normally distributed and you're missing like 30% of those values, so what you can do is you can fit a normal distribution to the available 70% and sample from that normal distribution to fill in the 30%, right? This will not be applicable for most situations because most columns are not supposed to be normally distributed. But if you know how your data is supposed to look like, you can fabricate data to fill in those missing values. This is much harder than I'm making it sound, but according to my limited knowledge, that's the only proper way to fill in missing values. And in general cases.
Okay. So the next question we have is from Arish, and he's asking that do all machine learning techniques have different libraries which I have to use while training and testing? If yes, where I can find it, and on which basis I can select that particular library?
Um, so not really, but sort of. So this distinction is more like, if to answer this question, I have to explain the difference between R and Python a little bit. In Python, the standard library is scikit-learn, and for 99% of the general use cases, except for deep learning, scikit-learn has whatever you need. Scikit-learn has more than what most people need. Um, and if you know the boundaries of what scikit-learn can do, you will be set. In R, it's a little different, because R, the philosophy of the language is slightly different. It's very uncommon to have like massive libraries in R, similar to how scikit-learn is. Scikit-learn is a huge library just because it has all these models, right? In R, you have smaller libraries, like there's one library which has generalized linear models. There's another other library which has trees. I think it's carrot or cart. I don't remember. It's been a while. Anyway, so in R, it's a little bit different, but the actual language syntax for R is much simpler, um, than Python for beginners, at least. And you don't have to remember the libraries. You have to remember the name of the model in R, or at least the function name. So that makes it a little bit easier as well. So yeah.
Okay. So let me look at what other questions do we have. Okay, so there's a question from Hassan, and he's asking that what kind of challenges you deal with as a data scientist, like what kind of problems you face the most in day-to-day operations.
Honestly, it's like this talk was about code and libraries and all that. Most of the problems in my job don't really have anything to do with programming. It's very like, I've been like working for 1 year and a few months, and only once did I have an actual programming problem. Only once. Um, all the other problems are either implementation problems or communication problems, or problems with the data that I get from the client. And dealing with all that is also a job. It is also part of my job description. Like, I can't just sit there and write code. I'm not a software engineer. I don't get paid for the code I write. I get paid for the stuff that my code does, right? That's a distinction, and I think that's very important. And just because of that, most of the problems aren't code related. I have to explain what I'm doing, or I have to explain why something that we thought we could do 2 weeks ago, now we've realized we can't do because we understand the data much better, or different things. This is most of the problems I have are like this.
Okay, so that was the last question, Rabeez. Thank you so much for such an insightful session, and thank you for all of those who joined in. We will have a YouTube video available soon, and for those who have shared their email addresses with us using the registration link, we will be emailing you those videos. And for the lucky draw winners, we will be reaching to all of you soon, so you can have a one-on-one session with Rabeez. So maybe make a list of questions you want to ask him, and we'll definitely be reaching out to all of you soon. So for the learning series, we have more sessions coming up. Make sure you keep checking out the page. They will be related to different topics, but the next 2 to 3 sessions will be based on machine learning and data science. So if you are interested, make sure that you do sign up for those sessions, and have a great day or night wherever you are, depending on the time zone. Thank you, everyone.